Hi everyone. So today we're gonna talk about an interesting topic, I think, which is called instruction level dependency, and it's gonna be in the context of high-level languages, and the examples are gonna be in C sharp, but it's mostly in the context of high-level languages. Because the interesting fact of life is that you're not gonna find any information about this topic in the context of high level languages. What you're gonna find about instruction level dependency is a lot of examples in C, C++, and like the most knowledge you're gonna find around this topic is assembly language and like processor level stuff, which is really low. And you might think that it doesn't make sense to talk about this in the context of C sharp or Java, for example, right? Well, let me convince you otherwise, and we're gonna see how instruction level dependency is related to all of the languages, not only low level stuff, but high level stuff as well. And we're gonna talk about what it is, how to break dependency chain, and what it's for. So let's actually jump in and let's ask ourselves why we would want to know about any sort of data or instruction level dependencies. And yeah, why? Why really? Well, it's performance, performance, performance. So each time you try to do this, you're actually caring deeply about your algorithm's performance. So let me give you an example what is a dependency and what actually is a dependency chain. So for example, if you have a loop and that loop actually goes through an array, and that array of numbers, and each iteration of the loop, you're just going to increment the counter. Well, you might think that processors will actually like schedule the increment instruction, then execute it, and then they're gonna recall that and do that again and again and again for each iteration of the loop, right? Well, wrong. That's not what happens because current processors have pipelines, and these pipelines have something that are called pipes or ports, and what they actually are is they're actually multiple channels where you can execute multiple instructions at the same time. So these ports are very specialized. So there's a couple of ports that actually handle different sort of instructions. And for most current processors, for example, if you're caring about incrementation of the loop or any sort of like mathematical operations, that processor is going to have 4 ports to be able to do that. So in theory, and in practice really as well, you can do 4 operations at the same time. But there's a catch. The catch is you can do that, but that data doesn't, well, if it has like dependencies, so your increment depends on some value that has to be calculated elsewhere, well, that's a data dependency, and therefore we cannot do it because we're going to run into trouble. So what we want to do is to actually identify these sort of quote unquote chains, and we're going to have a look how to break them. But let's see what are the dependency types. So what we have is a true dependence, which means that your write is actually dependent on a read that has to happen or just happened. We have the anti-dependence, which actually is the opposite, which means that your read actually depends on the write that just happened in like previous statement, right? Then we have what we can call an output dependence, which means if you have a single variable and you want to like increment that a couple of times, well, your increment depends on the previous increment, like it has to complete, right? And then we have what we can call a loop carried dependence, which means that multiple statements in the loop depend on each other, and sometimes they depend on previous iterations or actually next iterations of the loop. And last, we have control dependence, which means that our dependency chain is dependent on some if instruction that has to execute, and we're gonna go into one way or the other. All right, so these are the basic 5 dependency types. There's actually more dependency types, but they're exotic. and like 99% of your code base will be composed of these 5 dependency types. All right, so I guess let's jump into some code and let's see how we can optimize stuff. So like I said, let's actually start with the simplest algorithm that I can actually imagine. So we have like a simple and a single variable here called a, and we have a loop. And in each iteration, we're actually gonna increment this variable 4 times. Then we're gonna return the result, and that's it. So right off the bat, it would seem that there is absolutely no way to make this faster because it's so simple that there's nothing that you can do to make this faster because it's just a simple loop, right? And 4 increments. Well, we can actually do better. But let's measure the performance of this first. So around 200 milliseconds. Okay, how can we do better? Well, this is an example of what we can call an output dependency, which means that each write, subsequent write is dependent on the previous one completing, which means that we cannot actually schedule 4 things at the same time because we have to wait on these to complete. So we're doing one operation at a time in this loop, pretty much. How can we do better? Well, we can make them independent by actually having not a single variable but 4. And then, in order to get the same result, we're gonna add all of these variables here when we return the value. And like I said, we're gonna declare 4 of them. So we have 4 independent counters right now, and we're gonna increment them individually. So they're not dependent on each other right now. And at the end, we're gonna just do a sum. Okay, and let's see how this version actually performs. So the last version, almost 200 milliseconds. The independent one, 78. Well, that's actually 2.5 times faster, which is good, right? That's pretty good for such a small change, really. But this example is so simple that it's really hard to find examples like that in your code to actually optimize. So let's actually look at something different, something that actually has more utility, which for example is this sum function here, where we're just gonna have an array. We're gonna have a single variable called sum, and then in each iteration we're gonna sum over this array. Of course, we should actually return results, and that will be it. But let's actually, before we start to optimize this, let's actually, you might be wondering, or you might be asking, um, why doesn't the compiler actually help me in breaking these chains here, right? Because this is so simple that it should be broken. Well, the answer is the compilers actually helped you with breaking these chains, but they only can do so much. So in this example, this chain wasn't broken at all. But the reason is that, like I said, compilers in terms of like optimizations help you, but only do like 1% of the common cases in optimizations. If you want to be like very serious about optimizations, 99% of the time you have to implement it yourself. And it's because the compilers don't have enough context to be able to optimize all of this stuff, and that's why. There's central languages like C#, for example, which have just-in-time compilers, which in theory have more information when they compile, so they could actually emit more optimized code. But that's gonna be like a jump from 1% to 2%. There's like compilers that actually do a lot of things like Rust as well, which has this concept of zero cost abstractions. That might give you perhaps just a tiny bit more, but still it's gonna be like 1 to 2%. So the rest you have to do yourself, and that's just it. There's no way around it because the compilers will never have enough information to be able to optimize your code magically, and it's gonna be all good, right? All right, so let's move to the sum function. And like I said, we have the sum here. Nothing really complicated is happening here. And the question now is, can we do better? Well, we can do better. There's actually a couple of techniques that we can use to do better. So one of the techniques is that we can actually have multiple statements here instead of one, because jumps cost. And for perhaps what we can do here is we can sum 4 times, and that should be better, right? And then we're gonna sum the remaining residuals, right? So now this optimization means that we have this is called loop unrolling, by the way, and we sum over 4 times, and then we jump. We check this condition, sum 4 times, jump, check conditions, and so on. Should be faster. Let's see how much. So this actually took almost a second, and this takes 800. So a bit better, just a tiny bit better. We can still do better. So as we can see here, all of this is dependent on the sum. So we can actually apply the same technique that we used before. We can have not a single sum, but multiple sums. So for example, here we're going to split our sum into 4 individual sums. And then we're just going to simply increment each, sum the residuals again, and then we're just going to sum at the end, and that's it. So let's see how this performs. Well, it's better. Actually, that's not the right function. Let me test this function. It's pretty good, right? It's pretty good. Okay, so that's still not all of the optimizations that we can do here, because as it turns out, single statements can have dependency chains. So for example, this is a dependency chain here because we have to accumulate this, then this, then this, then this, so we have to wait on these, right? So what we can do is we actually can be clever about it and do some parentheses, and now we can actually do this and this at the same time, which is faster, but since this is just a simple and a single statement, we're not going to have like huge performance benefits. That might be like 1 millisecond or something like that. So it's not really something that we have to be, we have to care a lot about. Okay, so let's look at another example, which might be a tiny bit more difficult. So let's just say that we have again an array, and we want to find the minimum value of that array. So we have this min function here, and we're just going to return that. And what's the problem here with this here? So we have a dependency on between min and min itself. And again, how do we break this dependency chain? Well, again, we can apply the same trick where we just gonna say that we have multiples of min, and we're gonna do a min function with each of these, and then we're gonna actually min like the remainder, right? Okay, so this is a bit different because we're not using the built-in function. We're using this, actually we should be using this version, branch free. And why is that? Why we should be using this instead of like this mathmin here? Well, because this mathmin actually is using a branch. So we're gonna optimize everything, but we're gonna stall on the branch prediction because it's purely dependent on data, and if we're gonna have a lot of misses, then well, we're just gonna stall, and that's not good. So what we're trying to do here is we're trying to remove all of the if statements from our loop, which is not free because we have to now do all of these operations here and they're costly. But hopefully, if our data set has a lot of like uniform data, then we're gonna see performance improvements because still this is expensive, but having a branch misprediction is even more expensive. So let's see how these two perform. And like I said, if we're gonna have just a, for example, 0 here, that first function is gonna do awesome, right? Because, well, there's no like, we're always gonna be hitting our correct branch, so whatever. But if we're gonna say that our data is somehow like uniform, it's not really predictable, it's really hard to guess the correct branch, well, then things might be a little different. So let's run the first version. And that took 136 milliseconds. And the second version took a bit faster, 112. So again, we're actually paying the cost of that min function. And the question is, can we do better? Well, the answer to that question, of course, is yes, we can still do better. There's a hardware instruction, actually, that will do our min function. So we can optimize this further by actually not using this extraction, but using a AVX instruction, which has implemented a hardware min. I'm not gonna get into this implementation now, but as you can see, still we're actually getting a performance improvements, and we can actually still optimize this branch-free version to be even faster, to actually have different operations. So the last thing that actually is here to sort of explain is this aggressive inlining, and inlining actually means that the compiler will take this code and actually put it into that loop inside. And the reason for this is that we don't want to pay the cost of jumping to a function and then executing the function and going back. So this is really simple, and we want to have that code inlined in our loop. Okay, so that's pretty much it. Let's actually do like one final test and see how the characteristics change when we change our data sets. 143, 113. So as you can see here now, it's really hard to test branching code because processors are really good at branch prediction, and it's actually independent of the process that's being run, really. So they're gonna guess really good, right? And yeah, so that's all for now. Like I said, we could still do better if we wanted to, but that is an AVX instruction, and probably I'm gonna implement that and put it into like another video perhaps. And yeah, I guess that's it. So I hope that now you can see that this actually provides a lot of benefit, and give a thumbs up if you think it's something worthwhile. So yeah, thanks. That's all for now. Bye.